Imagine a cosmic explosion so immense that it painted the daytime sky for weeks, an event witnessed nearly 1,000 years ago, birthing what we now know as the Crab Nebula. This isn't just another pretty picture from space. It's a swirling cauldron of mystery, a place where the known laws of physics are constantly tested. The Crab Nebula is a cosmic wonder, a testament to the universe's power and strangeness. Within its colorful tendrils and energetic heart lies not one, not two, but 50 bizarre phenomena that continue to baffle scientists and ignite our imaginations. From its violently spinning core to its ever-expanding edges, this nebula presents puzzles at every turn. Join us as we embark on a journey through the Crab Nebula's most perplexing enigmas, a countdown of the 50 strangest aspects of this cosmic beacon, where every anomaly opens a door to deeper questions about the universe. Prepare to question everything you thought you knew as we unravel the mysteries of the crab, beginning with its central powerhouse and its peculiar behavior. Shifting our gaze to the heart of this nebula, we encounter phenomenon number 1, the pulsar's unexplained flickering. At the Crab Nebula's core resides a neutron star known as Pulsar B0531+21, a cosmic lighthouse emitting highly regular pulses of radio waves and X-rays. This pulsar is not just any ordinary celestial beacon. It's a rapidly spinning remnant of the very supernova that created the nebula, and its rhythmic emissions are astonishingly consistent, like a clock ticking in the vastness of space. However, this metronomic precision is occasionally disrupted by unpredictable flickers and glitches. These anomalies are brief, sudden changes in the pulsar's rotation speed and pulse timing, and they present a significant puzzle to astronomers. What causes these seemingly random hiccups in such an otherwise orderly system? Several theories have been proposed to explain these enigmatic glitches. One leading hypothesis suggests that these flickers are caused by crustal movements on the surface of the neutron star, often referred to as starquakes. These movements, though minuscule on a cosmic scale, could momentarily alter the pulsar's magnetic field and rotation, leading to observable changes in its pulses. Another theory involves the internal dynamics of the neutron star's magnetic field. Neutron stars possess incredibly strong magnetic fields, and it's believed that reconfigurations within these fields could release bursts of energy, affecting the pulsar's rotation and emissions. These magnetic field reconfigurations might be similar to solar flares on our Sun, but on a vastly more energetic scale. Visualizations of the pulsar's light curves could illustrate these glitches, showing the sudden spikes and dips in intensity. Diagrams depicting potential glitch mechanisms, such as crustal deformations or magnetic field line reconnections, would further enrich the explanation. As we continue to probe the mysteries of the Crab Nebula, the erratic behavior of its central pulsar serves as a constant reminder of the complex and often baffling nature of the cosmos, bringing us to the next perplexing phenomenon within this cosmic wonder. Transitioning from the perplexing pulsations, our exploration now takes us to another mind-bending aspect of the Crab Nebula, phenomenon number 2, the superluminal motion of plasma ejections. Here, we encounter a cosmic illusion that challenges our understanding of speed and light. Within the Crab Nebula, astronomers have observed plasma jet streams of superheated gas that appear to be moving faster than the speed of light. This observation might seem to defy Einstein's theory of relativity, which states that nothing can exceed the speed of light in a vacuum. However, before we rewrite the laws of physics, it's essential to understand that this apparent superluminal motion is an optical illusion, a trick of perspective caused by the jet's angle relative to Earth. To grasp this concept, imagine a car traveling at a constant speed, but at an angle towards you. If the car were moving directly across your field of vision, you would observe its true speed. However, if it's moving at an angle, some of its motion is directed towards you, shortening the apparent distance it covers from your vantage point. In the case of the plasma jets in the Crab Nebula, these jets are ejected from the central pulsar at very high speeds, but not exceeding the speed of light. The illusion arises because these jets are moving at a significant fraction of the speed of light and at a small angle to our line of sight. This particular alignment causes us to underestimate the time it takes for the plasma to travel a certain distance across our view, making its apparent speed seem much faster than it actually is. The geometry of this phenomenon is crucial. If the angle is just right, the perceived transverse velocity can greatly exceed the actual velocity of the ejected material. This effect is purely visual, a consequence of how we observe the motion from Earth. The actual velocities of these ejections are still incredibly high, often a significant fraction of the speed of light, but they do not break the cosmic speed limit. Animated diagrams can effectively illustrate how superluminal motion occurs, showing the true path of the plasma jet versus its apparent motion as seen from Earth. Real images of these plasma jets underscore the visual evidence of this phenomenon, showcasing the dynamic and relativistic processes at play within the Crab Nebula. As we unravel this cosmic illusion, it becomes clear that the universe is full of surprises, inviting us to view familiar concepts from new and unexpected angles, which sets the stage for our next investigation into misaligned emissions. Departing from optical illusions, let's turn our attention to a set of puzzles that delve deeper into the Crab Nebula's composition and emissions. Phenomena number 3 and 4, the misaligned X-ray and optical emissions, and the unexplained composition of its filaments. These phenomena highlight the complexities within the nebula, challenging our understanding of its physical and chemical processes. One of the intriguing aspects of the Crab Nebula is that its X-ray emissions do not perfectly align with its optical light distribution. If the processes emitting X-rays and optical light were perfectly correlated, we would expect to see a similar pattern in both types of images. However, observations reveal discrepancies, with certain regions appearing brighter in X-rays than in optical light, and vice versa. This misalignment suggests that different mechanisms or particle distributions are responsible for these emissions. X-rays are typically produced by highly energetic particles, such as electrons, spiraling through magnetic fields, a process known as synchrotron radiation. Optical light, on the other hand, can be produced by various processes, including thermal emission from hot gas or synchrotron radiation from less energetic particles. The mismatched alignment implies that the distribution of these high-energy particles and the conditions that give rise to these emissions vary throughout the nebula. Some areas might have a higher concentration of extremely energetic electrons, leading to stronger X-ray emissions, while others may have more of the conditions favorable to optical light. Adding to the puzzle is the unusual chemical makeup of the Crab Nebula's filaments. These filaments are the remnants of the original star that exploded, forming the nebula. They consist of various elements such as hydrogen, helium, carbon, oxygen, and heavier elements forged in the star's core. However, the ratios of these elements are not what scientists would typically expect. Some elements are present in unexpectedly high or low concentrations, defying simple explanations based on stellar evolution and supernova nucleosynthesis. The atypical composition of the filaments suggests a complex history of element formation and mixing within the progenitor star and during the supernova explosion. It could also indicate that certain processes within the nebula, such as interactions with the central pulsar's wind, have altered the chemical composition of the filaments over time. Understanding the exact chemical makeup of these filaments requires detailed spectroscopic analysis and careful modeling of the nebula's physical conditions. Visuals of X-ray and optical overlays can dramatically illustrate the misaligned emissions. These composite images reveal the regions where X-rays and optical light coincide and where they diverge, providing a clear picture of the emission discrepancies. Diagrams showing filament composition can further highlight the unusual elemental ratios, making it evident that the Crab Nebula is far from a simple, uniform structure. The journey uncovering origins promises increasingly strange encounters as we now consider the dynamic wisps, jets, and toruses within. Now, shifting our gaze closer to the heart of the Crab Nebula, we encounter a trio of dynamic and enigmatic features: the wisps, the jets, and the torus. Each of these components displays behaviors that continue to puzzle astronomers and challenge our understanding of the nebula's inner workings. The wisps are among the most intriguing features in the Crab Nebula. These are highly variable, moving structures located in the vicinity of the central pulsar. They appear as delicate, shimmering bands of light that constantly change in brightness and position. The wisps seem to emerge, brighten, fade, and even disappear over relatively short timescales, sometimes within days or weeks. Their dynamic nature suggests that they are closely linked to the activity of the pulsar, but the exact mechanisms behind their formation and movement remain uncertain. One theory suggests that the wisps are formed by shockwaves created as the pulsar's wind interacts with the surrounding nebula. These shockwaves could compress and accelerate particles, causing them to emit synchrotron radiation and become visible as wisps. However, the details of this process, such as the precise conditions required for wisp formation and the role of magnetic fields, are still debated. Emanating from the pulsar's poles are jets, streams of particles and energy that shoot out into the nebula at high speeds. These jets are a common feature in many pulsars and neutron stars, but the Crab Nebula's jets exhibit surprising instabilities. Instead of being smooth, continuous flows, they often appear broken, fragmented, or even twisted. These instabilities suggest that the jets are subject to complex forces, such as magnetic fields, pressure gradients, or interactions with the surrounding nebula material. Understanding the origin and nature of these instabilities is crucial for understanding how the pulsar transfers energy to the nebula. Finally, the Crab Nebula features an inner torus, a donut-shaped structure that surrounds the pulsar. The torus is thought to be formed by the pulsar's wind, which is channeled and compressed in the equatorial plane. The torus is not a static structure. It continuously changes in shape and brightness. These dynamic changes could be due to variations in the pulsar's wind output, changes in the magnetic field configuration, or interactions with the surrounding nebula. Time-lapse imagery of these features vividly illustrates their ever-changing nature, revealing a dynamic and turbulent environment shaped by the pulsar's immense energy output. As we consider the wisps, jets, and torus, it becomes clear that the Crab Nebula is far more than just an expanding cloud of gas and dust. It is a complex, dynamic system driven by the energy of its central pulsar, leading us to consider the nebula's overall expansion and magnetic fields. Turning our attention outward, let's consider the Crab Nebula's overall growth and the intricate magnetic fields that permeate it. The Crab Nebula is in a perpetual state of expansion, growing larger as time passes. This expansion isn't just a simple outward motion. It's a complex interaction between the nebula's internal pressure and the external environment. By studying the rate at which the nebula expands, astronomers can gain valuable clues about its age and the amount of energy injected into it by the central pulsar. However, the expansion rate also raises questions about how the nebula interacts with the surrounding interstellar medium. Is the nebula plowing through the interstellar gas, or is it expanding into a relatively empty region? These interactions can affect the nebula's shape, density, and even its eventual fate. Visualizations of the nebula's expansion over time clearly show how its size and shape have changed since the initial supernova event almost 1,000 years ago. Adding to the nebula's complexity is its tangled and powerful magnetic field. This magnetic field plays a crucial role in many of the phenomena observed in the Crab Nebula, from the acceleration of particles to the confinement of the pulsar's wind. The magnetic field is not uniform or orderly. Instead, it is a chaotic web of field lines that twist and turn throughout the nebula. This tangled structure is thought to be generated by the turbulent motions of the plasma within the nebula and the pulsar's spin. Mapping the full structure of the magnetic field is a daunting task, but astronomers use a variety of techniques, including radio polarimetry and X-ray observations, to piece together its overall configuration. Understanding the magnetic field is essential for understanding how particles are accelerated to near-light speeds within the nebula, leading us to the enigma of high-energy particles. Now, let's turn our attention to some of the most energetic aspects of the Crab Nebula. The Crab Nebula stands as a colossal particle accelerator, catapulting particles to velocities nearing the speed of light. However, the precise mechanisms and locations where this acceleration occurs remain subjects of intense debate. While it's clear that the nebula is a powerhouse of high-energy activity, the specifics of how particles gain such tremendous speeds are still not fully understood. Adding to the intrigue is the mystery of the missing positrons. In theory, particle acceleration should produce equal numbers of electrons and positrons, their antimatter counterparts. Yet, observations reveal a significant deficit of positrons compared to electrons in the nebula. This discrepancy has led to various potential explanations, one being positron annihilation. Positrons, upon encountering electrons, can annihilate each other, converting their mass into energy in the form of gamma rays. Another possibility is that positrons somehow escape the nebula more readily than electrons, perhaps due to differences in their interactions with the nebula's magnetic field. To better understand these phenomena, scientists have developed various models of particle acceleration within the nebula. Some models propose that particles are accelerated in the vicinity of the pulsar, where the rapidly rotating magnetic field generates strong electric fields. Other models suggest that particle acceleration occurs in the nebula's shock waves, where fast-moving material collides with slower-moving gas. Visualizations of high-energy particle distributions show that these particles are not uniformly distributed throughout the nebula, but tend to concentrate in certain regions, possibly near the pulsar or along the edges of the nebula's jets and wisps. As we continue our exploration, up next are the Crab Nebula's gamma-ray flares and the unknown mechanisms behind them. Turning our gaze towards another high-energy puzzle, we find the Crab Nebula's gamma-ray flares and the unknown mechanisms behind them. The Crab Nebula is not just a steady beacon of radiation. It occasionally erupts with unpredictable and intense gamma-ray flares. These flares are short-lived bursts of extremely high-energy light that defy conventional explanations of how the nebula operates. What makes these flares so puzzling is their intensity and rapid onset, which challenge our understanding of particle acceleration and energy release in extreme environments. Pinpointing the exact mechanism behind these flares has proven difficult, leading to several theoretical explanations. One potential mechanism involves magnetic reconnection events. In this scenario, magnetic field lines within the nebula become twisted and tangled, storing vast amounts of energy. When these field lines suddenly realign, they release this stored energy in a burst of particle acceleration, resulting in a gamma-ray flare. Another proposed mechanism is sudden particle acceleration bursts, where a rapid change in the nebula's magnetic field or plasma environment causes a surge of particle acceleration, leading to a flare. Modeling these flares presents significant challenges due to the complex physics involved. Scientists use computer simulations to recreate the conditions within the nebula and test different flare mechanisms. These simulations often involve mapping gamma-ray flare intensities over time, which shows the rapid increase and subsequent decay of the flare's brightness. Additionally, diagrams of possible magnetic reconnection scenarios help visualize how magnetic field lines might interact and release energy. Despite these efforts, the exact trigger and dynamics of the gamma-ray flares remain an open question, pushing the boundaries of our knowledge about extreme astrophysical phenomena. With the gamma-ray flares explained, we now focus on the puzzling anisotropic distribution of accelerated particles within the Crab Nebula. Transitioning from flares to the subtle patterns within, the anisotropic distribution of accelerated particles represents another layer of complexity in the Crab Nebula. Unlike a uniform distribution where particles are evenly spread, the Crab Nebula exhibits anisotropy. This means that accelerated particles are not evenly distributed. Instead, they show a preference for certain directions and locations within the nebula. This uneven distribution significantly affects the nebula's emission patterns, because high-energy particles emit radiation as they spiral along magnetic field lines. Regions with higher particle densities will appear brighter and emit more intensely at specific wavelengths, such as X-rays and gamma rays. Conversely, areas with fewer accelerated particles will appear dimmer. This creates a mottled appearance in images of the Crab Nebula, with bright knots and filaments contrasting against darker, less active regions. The anisotropic distribution implies important details about the acceleration processes at play. If particles were accelerated uniformly, we'd expect to see a more even glow across the nebula. The fact that we observe preferential directions suggests that acceleration mechanisms are localized and directional. For example, the pulsar's jets and the shockwaves they create are thought to be prime locations for particle acceleration. Particles accelerated in these areas tend to follow the magnetic field lines, leading to concentrated emission along those paths. To visualize this, astronomers create maps showing the non-uniform distribution of particle energies and densities. These visualizations often use color coding to represent the intensity of radiation at different points within the nebula, revealing the spatial variations in particle populations. Such maps provide insights into the underlying acceleration processes and help scientists refine their models of the Crab Nebula's complex dynamics. As we dissect the distribution of particles, it's impossible not to consider the profound connection between the pulsar wind and the nebula's unique morphology. Exploring the connection between the pulsar wind and the nebula's morphology reveals a dynamic interplay shaping the Crab Nebula's very essence. The pulsar wind, a relentless outflow of high-energy particles and magnetic fields from the central pulsar, carves and molds the surrounding nebula material. This wind isn't just a gentle breeze, it's a hurricane of energy that dictates much of what we observe. The interaction between the pulsar wind and the material ejected during the original supernova is complex. As the wind slams into the slower-moving ejector, it creates a termination shock. This shock heats the material to extreme temperatures, causing it to glow brightly in X-rays and other high-energy wavelengths. The shape of this termination shock and the subsequent flow of material influences the overall form of the nebula. What remains unknown is the precise mechanism by which the pulsar wind transfers its energy and momentum to the nebula. Scientists are still working to understand how the wind interacts with the tangled magnetic fields and turbulent plasmas within the nebula. This interaction determines the acceleration of particles to cosmic ray energies and the distribution of energy throughout the structure. Simulations of pulsar wind interaction with the nebula's environment offer a glimpse into these processes. These models show how the wind inflates a bubble within the supernova ejector, creating a complex network of shocks and filaments. By comparing these simulations with actual observations, astronomers can refine their understanding of the underlying physics. These simulations, while informative, continue to evolve as new data emerge. With those simulations in mind, we now explore the variations in the nebula's radio emission. Transitioning our focus from the shaping forces of the pulsar wind, we now consider the variations in the nebula's radio emission and its potential dance with pulsar activity. The Crab Nebula doesn't just shine steadily in radio waves. Its radio emission fluctuates, brightening and dimming over time. Scientists are keen to determine if these changes are merely random noise or if they're linked to the behavior of the central pulsar. The nebula's radio emission is not constant but varies over time, showing subtle but measurable changes in its intensity. These variations can occur on timescales from days to years, presenting a complex puzzle. Understanding what drives these changes could reveal more about the inner workings of both the nebula and the pulsar it houses. Whether these variations are linked to changes in the pulsar's behavior, such as glitches or other sudden events, is still an active area of research. Pulsar glitches, sudden spin-ups of the pulsar, could potentially inject energy into the nebula, affecting its radio emission. If a correlation exists, it would provide valuable insights into the energy transfer mechanisms at play. Data plots showing radio emission variability over time are often compared with records of pulsar glitch events. These comparisons look for any temporal correlations between the two phenomena. While some studies have suggested a possible link, the evidence remains inconclusive, and more data is needed to establish a definitive connection. The search for a correlation between the nebula's radio emission and pulsar activity continues to be a fascinating pursuit in unraveling their intertwined destinies. From radio waves, we move on to consider the infrared spectrum of the Crab Nebula and what it reveals about the dust it contains. Turning our attention now to a different wavelength, let's explore the Crab Nebula's infrared spectrum, the unidentified mechanism responsible for heating its dust, and how temperature differs across its dusty expanse. The Crab Nebula emits a rich infrared spectrum, revealing the presence of dust grains that absorb and re-emit energy at these longer wavelengths. This infrared glow provides crucial information about the composition, distribution, and temperature of dust within the nebula. The emission from dust grains in the Crab Nebula is a key component of its infrared signature. These tiny particles, composed of materials like silicates and carbon compounds, absorb ultraviolet and visible light from the central pulsar and other sources. They then re-emit this energy as infrared radiation, contributing significantly to the nebula's overall luminosity in the infrared. What exactly heats this dust remains a fascinating mystery. One possibility is ultraviolet radiation from the central pulsar. The pulsar emits a tremendous amount of energy across the electromagnetic spectrum, including intense ultraviolet radiation that could heat the dust grains. However, it's not clear if the pulsar's ultraviolet output is sufficient to account for the observed dust temperatures. Alternative sources of heating might include collisions with energetic particles or other radiation mechanisms within the nebula. Infrared images reveal the distribution of dust and temperature variations. These images show that dust is not uniformly distributed but appears in clumps and filaments throughout the nebula. The temperature of the dust also varies, with some regions being warmer than others. These temperature variations can provide clues about the sources of heating and the physical conditions within the nebula. The dust's temperature distribution and the source of its heating remain open questions, inviting further research to understand how energy flows through the Crab Nebula. From heated dust, let's consider the nebula's larger environment, specifically the Crab Nebula's location within the interstellar medium and the effects of the supernova explosion on the surrounding gas. Now shifting our gaze outward, let's examine the Crab Nebula's location within the interstellar medium and the profound effects the supernova had on its surroundings. The Crab Nebula is not isolated. It resides within the vast expanse of the interstellar medium, which is the sparse collection of gas and dust that fills the space between stars in our galaxy. Its precise location influences how we observe and understand it. The nebula's interaction with this medium affects its expansion, shape, and the distribution of its material. The supernova explosion that birthed the Crab Nebula sent shockwaves rippling through the surrounding interstellar gas and dust. These shockwaves compressed and heated the gas, causing it to glow and altering its composition. The expanding shockwave also swept up interstellar material, mixing it with the ejecta from the supernova. This interaction creates a complex interplay between the nebula and its environment. The impact of the supernova on the surrounding gas goes beyond mere heating and compression. The high-energy particles and radiation from the supernova can ionize atoms and molecules, changing the chemical properties of the interstellar medium. This can lead to the formation of new molecules and the destruction of others, further altering the composition of the gas. The interaction between the Crab Nebula and the interstellar medium is a dynamic and evolving process, one that continues to shape the nebula's appearance and behavior today. As the expanding supernova remnant plows into the interstellar medium, it creates observable structures such as shock fronts and regions of enhanced density. Wide-field images showcasing the nebula's surroundings and computer simulations illustrating the propagation of supernova shockwaves visually confirm these effects. These images provide context and allow us to better understand the nebula's place within the larger galactic environment. Understanding this interaction is vital for piecing together the complete story of the Crab Nebula, which leads us to the complex challenges of discerning its three-dimensional structure through the use of tomography. Turning our attention now to the nebula's physical form, the three-dimensional structure of the Crab Nebula presents a formidable challenge to astronomers. The difficulty in understanding the nebula's true shape and depth arises primarily from projection effects. When we observe the Crab Nebula from Earth, we are essentially viewing a complex three-dimensional object projected onto a two-dimensional plane. This projection makes it incredibly difficult to discern the true spatial relationships between different features within the nebula. What appears to be close together in our line of sight may actually be separated by vast distances within the nebula's volume. To overcome these limitations, astronomers employ tomographic techniques to reconstruct the three-dimensional structure from multiple viewing angles and spectral data. Tomography in astronomy involves combining observations taken from different vantage points or using different wavelengths of light to build a comprehensive model of the nebula. This approach is similar to how medical tomography, like computed tomography scans, creates three-dimensional images of the human body from a series of X-ray images. These models offer unprecedented insight into the nebula's complex morphology, including the distribution of its filaments, the shape of its central pulsar wind nebula, and the location of shock fronts and particle acceleration regions. The creation of these three-dimensional models often involves sophisticated computer algorithms and complex data analysis techniques. Astronomers also use spectral data, which reveal the velocities and compositions of the gas within the nebula, to further refine these models. By carefully analyzing the Doppler shifts of spectral lines, they can infer the motion of the gas along our line of sight, providing crucial information for reconstructing the nebula's three-dimensional structure. These complex methods and models reveal the intricacies of the Crab Nebula's form, which then begs the question of how the nebula interacts with external magnetic fields. Transitioning our attention to the forces acting upon the Crab Nebula, the Crab Nebula's interaction with external magnetic fields significantly influences its shape and dynamics. The nebula does not exist in isolation. It resides within the broader interstellar medium, which is permeated by magnetic fields. These external magnetic fields can exert pressure on the expanding nebula, affecting its overall morphology. Specifically, external magnetic fields can impede the nebula's expansion in certain directions, leading to an asymmetrical shape. If the external magnetic field is aligned in a particular direction, it can restrict the expansion of the nebula along that axis, causing it to elongate or flatten in other directions. This interaction can also lead to the formation of distinctive features, such as pinched or distorted regions in the nebula's outer boundaries. To better understand these complex interactions, astronomers employ numerical simulations that model the interaction between the nebula and external magnetic fields, which offer a powerful tool for visualizing and quantifying these effects. These simulations involve solving magnetohydrodynamic equations, which describe the behavior of electrically conducting fluids, such as the plasma within the nebula, under the influence of magnetic fields. By varying the strength and orientation of the external magnetic field in these simulations, researchers can explore a range of possible scenarios and compare the results with observed features in the Crab Nebula. These simulations reveal that the external magnetic field can not only deform the nebula, but also influence the distribution of energy and particles within it. Regions where the magnetic field is stronger may experience enhanced particle acceleration, leading to brighter emission in radio, optical, and X-ray wavelengths. Furthermore, diagrams showing how magnetic field lines might interact with the nebula illustrate the complex interplay between the nebula's internal magnetic field and the external magnetic field. These diagrams often depict the magnetic field lines bending and twisting around the nebula, creating regions of enhanced magnetic pressure and shaping the nebula's overall structure. These external magnetic fields can thus profoundly affect the Crab Nebula's expansion, morphology, and internal dynamics, highlighting the importance of considering its broader environment. Having shed light on the magnetic forces, it's time to look at how the nebula's heavy element distribution further reveals its secrets. Turning our gaze inward, the puzzle of the Crab Nebula's heavy element distribution presents a fascinating area of study. The nebula exhibits a non-uniform distribution of heavy elements such as iron and silicon, which are scattered unevenly throughout its structure. This irregular distribution suggests that different regions of the nebula have experienced varying degrees of nucleosynthesis and mixing. Understanding why these elements are not uniformly spread is crucial for unraveling the details of the supernova explosion that created the nebula. As for the origin of these elements, the heart of a massive star serves as the cosmic furnace where nuclear fusion forges heavier elements from lighter ones. This process occurs over millions of years, culminating in the star's eventual collapse and subsequent supernova. During the supernova, temperatures and pressures become so extreme that rapid nucleosynthesis occurs, creating a burst of heavy elements. These newly synthesized elements, including iron, silicon, and others, are then ejected into space along with the rest of the star's remnants. The role of the supernova in element synthesis cannot be overstated. The explosion is not merely a destructive event but also a creative one, enriching the surrounding interstellar medium with the building blocks for future generations of stars and planets. The amount and type of elements ejected depend on the mass and composition of the progenitor star, as well as the dynamics of the explosion itself. Element distribution maps and models of supernova nucleosynthesis help scientists piece together the events that occurred during the explosion. These maps, generated from observations across multiple wavelengths, reveal the spatial distribution of different elements within the nebula. By comparing these maps with theoretical models of supernova nucleosynthesis, astronomers can test their understanding of the physical processes at play and refine their models accordingly. The study of the Crab Nebula's element distribution, therefore, offers valuable insights into the inner workings of supernova and their profound impact on the chemical evolution of the universe. Now that we've considered the Crab's elemental composition, let's explore the nebula's evolution over time and what changes are predicted for its future. The evolution of the Crab Nebula over time offers a compelling look into the dynamic life cycle of supernova remnants. Since its explosive birth in 1054, the nebula has undergone significant changes that continue to intrigue astronomers. Initially, the rapidly expanding cloud of gas and debris was much smaller and denser. Over the centuries, it has steadily expanded, growing from a compact core to its current size, spanning approximately 11 light-years. This expansion is driven by the energy injected by the central pulsar, designated Pulsar Bravo 0531+21, which continuously emits a relativistic wind of particles and magnetic fields. As the nebula expands, its interaction with the surrounding interstellar medium becomes more pronounced. The outer edges of the nebula collide with this pre-existing material, creating shock waves that heat the gas and cause it to glow. These interactions also shape the nebula's overall morphology, influencing the distribution of filaments and other structures. The pulsar's energy output plays a critical role in this evolution. While the pulsar's rotation rate has gradually slowed down over time, it continues to inject a tremendous amount of energy into the nebula. This energy sustains the synchrotron radiation that makes the Crab Nebula visible across the electromagnetic spectrum, from radio waves to gamma rays. Looking to the distant future, astronomers predict that the Crab Nebula will continue to expand and evolve. Current models suggest that the pulsar's energy output will gradually decrease, leading to a decline in the nebula's overall brightness. As the pulsar's influence wanes, the nebula will become more diffuse, and its interaction with the interstellar medium will dominate its appearance. Eventually, the Crab Nebula will fade into the background, becoming a faint and unremarkable remnant of a once spectacular supernova. Simulated time-lapse sequences generated from observational data and theoretical models provide a captivating glimpse into this future evolution. These simulations show the nebula expanding and fading over thousands of years, its intricate structures gradually dissipating as it merges with the surrounding interstellar medium. Now that we've charted the Crab's past and speculated on its future, let's turn our attention to its X-ray spectrum and what it reveals about the energetic particles within. Turning now to another fascinating aspect, let's explore the Crab Nebula's X-ray spectrum, a key to understanding the energetic processes at play. The nebula's X-ray emission is primarily due to synchrotron radiation, a phenomenon produced by highly energetic electrons spiraling around magnetic field lines within the nebula. These electrons, accelerated to near light speed by the pulsar's intense electromagnetic fields, emit photons as they are forced to move in a curved path by the magnetic field. This process results in a continuous spectrum of radiation, spanning from radio waves to gamma rays, with the X-ray portion being particularly prominent. The distinctive shape of the Crab Nebula's X-ray spectrum offers valuable insights into the energy distribution of these electrons. The spectrum typically follows a power law distribution, meaning the intensity of the radiation decreases with increasing energy. The slope of this power law is directly related to the energy distribution of the electrons, providing clues about the acceleration mechanisms and the physical conditions within the nebula. Steeper slopes indicate a greater proportion of lower energy electrons, while flatter slopes suggest a more uniform distribution across a wider range of energies. X-ray spectroplots of the Crab Nebula reveal a wealth of information about the nebula's dynamics. By analyzing these plots, astronomers can determine the energy range of the emitting electrons, estimate the strength of the magnetic field, and probe the acceleration processes that boost these particles to such high energies. Diagrams illustrating synchrotron emission mechanisms further help visualize how these electrons interact with the magnetic field to produce the observed radiation. These diagrams show electrons spiraling along magnetic field lines, emitting photons in a cone-shaped pattern. The energy of the emitted photons depends on the electron's energy and the strength of the magnetic field, allowing astronomers to infer these properties from the observed X-ray spectrum. Having examined the Crab Nebula's X-ray emissions and their origins, let's consider the implications of these properties for other supernova remnants and whether the Crab can serve as a cosmic yardstick. Exploring the implications of the Crab Nebula's properties for other supernova remnants, studying this cosmic marvel provides invaluable insights into the broader family of stellar explosions. The Crab Nebula, with its well-documented history and ongoing activity, serves as a benchmark for understanding the dynamics, particle acceleration, and emission mechanisms in other, less studied supernova remnants. By comparing the characteristics of the Crab Nebula, such as its expansion rate, magnetic field strength, and particle energy distribution, with those of other remnants, astronomers can gain a deeper appreciation for the diverse range of phenomena that occur in these objects. The Crab Nebula's detailed observations, spanning decades and multiple wavelengths, offer a unique opportunity to test theoretical models of supernova remnant evolution. These models, which describe the interaction of the expanding shock wave with the surrounding interstellar medium, the acceleration of particles at the shock front, and the subsequent emission of radiation, can be rigorously tested against the Crab Nebula's observed properties. If a model accurately reproduces the Crab Nebula's behavior, it can then be applied with greater confidence to other remnants, even those with limited observational data. In essence, the Crab Nebula acts as a cosmic laboratory, allowing astronomers to refine their understanding of the fundamental processes governing supernova remnants. Turning toward the Crab Nebula's potential use as a standard candle, the possibility of using it for distance measurements has intrigued astronomers, although not without its challenges. Standard candles are celestial objects with known intrinsic brightness, allowing their distance to be inferred from their observed brightness. While the Crab Nebula's brightness is well studied, its unique characteristics, such as its non-uniform structure and complex emission mechanisms, complicate its use as a standard candle. Moreover, the Crab Nebula's brightness changes over time, making it difficult to establish a precise baseline. However, if these challenges can be overcome, the Crab Nebula could potentially serve as a valuable tool for measuring distances to other galaxies, particularly at intermediate distances where other standard candles, like Type 1, a supernova, are less effective. Data comparisons between the Crab Nebula and other supernova remnants reveal both similarities and differences. For instance, the Vela supernova remnant, another well-studied object, exhibits similar synchrotron emission and particle acceleration, but it is much older and less energetic than the Crab Nebula. By comparing the emission spectra, expansion rates, and magnetic field strengths of these two remnants, as well as others like Cassiopeia A, astronomers can develop a more complete picture of how supernova remnants evolve over time. These comparisons help to identify common underlying processes and to understand the factors that contribute to the diversity observed among these objects. As we continue our exploration, we will uncover further mysteries related to the mass of ejected material from the Crab Nebula. Transitioning to another perplexing aspect of the Crab Nebula, we confront the mystery surrounding the mass of the material ejected during the initial supernova explosion. Observed measurements indicate that the nebula's mass is less than what theoretical models predict. Scientists estimate the ejected material to be about 1 to 5 solar masses, a figure derived from analyzing the nebula's expansion rate, density, and composition. However, standard supernova models, which account for the star's initial mass and the energy released during the explosion, typically forecast a higher mass ejection, often ranging from 5 to 10 solar masses. This discrepancy presents a significant challenge to our understanding of supernova dynamics. The variance between observed data and theoretical predictions brings us to the missing mass problem within the Crab Nebula. Several hypotheses attempt to resolve this inconsistency. One potential explanation involves the presence of undetected material. It is possible that a portion of the ejected mass exists in a form that is difficult to observe, such as cold, neutral gas or dust located far from the nebula's central regions. These materials might not emit strong radiation, making them virtually invisible to current observational techniques. Another possibility suggests that some of the ejected mass may have already mixed with the surrounding interstellar medium, becoming indistinguishable from the ambient gas and dust. Alternatively, errors in the models themselves could contribute to the discrepancy. Supernova models are complex simulations that rely on numerous assumptions about the star's internal structure, nuclear reactions, and energy transport mechanisms. If these assumptions are not entirely accurate, the models may overestimate the amount of mass ejected during the explosion. For example, the models might not fully account for the energy lost through neutrino emission or the effects of turbulent mixing within the exploding star. Refining these models through improved computational techniques and a better understanding of the underlying physics is crucial for resolving the missing mass problem. Having now addressed these mass discrepancies, we will explore another captivating characteristic of the Crab Nebula: its influence on its surroundings and its ability to potentially foster the birth of new stars. Turning our attention to how the Crab Nebula impacts its cosmic neighborhood, we examine its influence on the surrounding environment and its potential role in triggering the formation of new stars. The Crab Nebula, far from being an isolated entity, dynamically interacts with the interstellar medium, or ISM, the sparse collection of gas and dust that permeates the space between stars. The nebula's intense radiation and powerful shock waves act as agents of change, influencing the ISM's physical and chemical properties. Specifically, the radiation emitted by the Crab's pulsar and the expanding nebula can ionize the surrounding gas, stripping electrons from atoms and molecules. This ionization process can alter the temperature and density of the ISM and potentially affect the structure and evolution of nearby molecular clouds. Moreover, the shock waves generated by the nebula's expansion ram into the surrounding ISM, compressing and heating the gas. These shock waves can propagate over vast distances, triggering a cascade of effects on the interstellar material. A key question is whether these compression events can initiate the gravitational collapse of gas and dust clouds, thereby leading to the formation of new stars. Star formation typically requires dense regions of gas and dust to overcome internal pressure and collapse under their own gravity. The shock waves from the Crab Nebula might provide the necessary external pressure to initiate or accelerate this process in certain regions. While direct observational evidence of the Crab Nebula triggering star formation is still limited, astronomers have identified potential star-forming regions in its vicinity. These regions often exhibit characteristics such as increased density, elevated temperatures, and the presence of young stellar objects, which are indicative of recent or ongoing star formation. Images from telescopes like Hubble reveal tantalizing hints of compressed gas clouds and protostars near the nebula's expanding boundaries. However, definitively linking these features to the Crab's influence requires further investigation, including detailed studies of the gas kinematics, chemical composition, and age distribution of the stellar populations. As we consider the chemical composition of the Crab Nebula, we also want to dive deeper into the nature of the chemical makeup and what that implies. Transitioning to a microscopic perspective, we explore the chemical composition of the Crab Nebula. An overview reveals a cosmic melting pot of elements, each with a story to tell about the supernova event that birthed the nebula. The Crab Nebula contains a wealth of elements including hydrogen, helium, carbon, oxygen, nitrogen, sulfur, silicon, and iron. However, it's the abundance of certain elements, or rather the ratios between them, that sets the Crab Nebula apart. For example, the Crab Nebula shows an overabundance of helium compared to hydrogen, which is not typically observed in other nebulae. This suggests that the progenitor star had undergone extensive nuclear fusion, converting much of its hydrogen into helium before the supernova. The presence of heavier elements like carbon, oxygen, silicon, and iron further enriches the nebula's chemical tapestry. These elements were primarily synthesized during the supernova explosion itself through processes like explosive nucleosynthesis. The distribution and abundance of these elements provide clues about the dynamics of the explosion, such as the temperature, density, and neutron flux in different regions of the ejecta. In comparison with other nebulae, the Crab Nebula stands out due to its relatively high abundance of heavy elements, particularly iron. This is indicative of a massive progenitor star that underwent significant nuclear processing before its explosive demise. When compared to other supernova remnants like Cassiopeia A or planetary nebulae like the Ring Nebula, the Crab Nebula exhibits distinct compositional differences. Cassiopeia A, for instance, shows a higher abundance of oxygen and silicon, suggesting a different type of progenitor star and explosion mechanism. Planetary nebulae, on the other hand, are typically enriched in carbon and nitrogen due to the nuclear processes in lower mass stars. The Crab Nebula's unique chemical signature, characterized by helium and heavy element enhancements, makes it a valuable benchmark for understanding the evolution and explosive death of massive stars. Delving further, there's a perplexing situation involving specific anomalies within the nebula's synchrotron spectrum. Diving into the spectral oddities of the Crab Nebula, we encounter another puzzling phenomenon. The synchrotron spectrum, which plots the intensity of radiation against its frequency, exhibits unexplained bumps that deviate from the expected smooth curve. In theory, the synchrotron spectrum should display a consistent decline in intensity as frequency increases, yet observations reveal unexpected peaks and troughs. These anomalies suggest complexities in the underlying emission mechanisms that are not fully understood. Exploring potential explanations, scientists have proposed several theories, none of which are definitively confirmed. One hypothesis suggests specific electron energy injections at certain frequencies. If there were localized regions within the nebula where electrons are being accelerated to particular energy levels, this could result in enhanced synchrotron emission at corresponding frequencies, creating the observed bumps. Another theory involves unique magnetic field configurations within the nebula. Variations in the magnetic field's strength and orientation could affect the energy and distribution of electrons, leading to irregularities in the synchrotron spectrum. Regions with stronger or more ordered magnetic fields might produce more intense synchrotron radiation, contributing to the spectral bumps. Spectral plots of the Crab Nebula's synchrotron emission clearly highlight these anomalies. The smooth, theoretical curve is contrasted by the jagged, observed spectrum, with visible peaks at specific frequencies. Analyzing these plots, researchers attempt to correlate the bumps with other known features of the nebula, such as the locations of high-energy particles or regions of intense magnetic activity. However, a comprehensive model that accounts for all the observed spectral irregularities remains elusive. The presence of these unexplained bumps underscores the complexity of the Crab Nebula and invites further investigation into the processes governing its synchrotron emission. Could these spectral anomalies be linked to the pulsar's activity, or do they reflect localized conditions within the nebula? As we continue to unravel the mysteries of the Crab Nebula, we shift our focus to how the central pulsar shapes the environment of the nebula. The 48th phenomenon centers on understanding the profound influence of the Crab pulsar on the surrounding nebula. The Crab pulsar, a rapidly rotating neutron star at the heart of the nebula, acts as an engine driving much of the activity observed. Its intense energy output, primarily in the form of a powerful magnetic field and relativistic particles, fundamentally shapes the environment and dynamics of the surrounding nebula. The pulsar emits a strong stellar wind composed of electrons and positrons moving at near light speed. This wind interacts violently with the slower-moving material ejected during the original supernova explosion, creating a complex network of shock waves and magnetic fields. These interactions are responsible for accelerating particles to extremely high energies, leading to the synchrotron radiation that makes the Crab Nebula so bright across the electromagnetic spectrum. The energy injected by the pulsar is not uniformly distributed. It is concentrated in certain regions, leading to the formation of structures such as the torus and jets. Illustrations detailing the pulsar's influence zone reveal a complex interplay of forces. The pulsar's immediate vicinity is dominated by its strong magnetic field, which channels the charged particles and confines them into a narrow outflow. As these particles stream outward, they encounter the reverse shock, where the pulsar wind slams into the slower-moving nebula material. This collision heats the particles and amplifies the magnetic field, further contributing to the synchrotron emission. The jets emanating from the pulsar's poles are particularly striking examples of its influence. These highly collimated streams of particles extend far beyond the main body of the nebula, interacting with the surrounding interstellar medium. The effect on the nebular material is dramatic. The pulsar's energy injection causes the nebula to expand continuously, although not uniformly. The inner regions are more dynamic, with constantly changing structures and intense particle acceleration. The outer regions are less affected, but still show evidence of the pulsar's influence through their overall shape and magnetic field configuration. This constant flux of energy from the pulsar ensures the nebula remains a dynamic and ever-evolving cosmic laboratory. As we continue our exploration of the Crab Nebula, we examine the nature of the faint optical halos surrounding the main structure. The 49th phenomenon explores the nature of the faint optical halos surrounding the Crab Nebula. These halos, often overlooked in standard images, extend far beyond the bright, well-defined core of the nebula. Their faintness makes them challenging to study, but they hold valuable clues about the nebula's past and its interactions with the surrounding interstellar environment. These optical halos are composed of extremely tenuous gas, primarily hydrogen and helium, that emits light through a process called recombination. This occurs when ionized atoms recapture electrons, and as these electrons cascade down energy levels, they release photons at specific wavelengths, creating the faint glow we observe. The distribution of this emission is far from uniform, with variations in brightness and structure that provide insights into the nebula's history. The origin of these halos is linked to the Crab Nebula's ejection history. During the supernova explosion in 1054, a vast amount of material was expelled into space. While much of this material now forms the bright central nebula, some of it was ejected with lower velocities, forming a more extended, diffuse cloud. Over time, this slower-moving material has interacted with the surrounding interstellar medium, creating the faint optical halos we see today. Wide-field images that capture these faint features reveal their true extent. They stretch several times the diameter of the main nebula, indicating that the original supernova explosion had a far-reaching impact on its surroundings. The halo's structure is complex, with filaments and diffuse patches that suggest interactions with the interstellar magnetic field and density variations in the surrounding gas. The potential formation mechanisms for these halos involve a combination of factors. The initial supernova ejecta likely contained a range of velocities, with the slower components forming the halos. As this material expands, it encounters the interstellar medium, leading to shocks and compression. These shocks can heat the gas, causing it to ionize and emit light. Additionally, the nebula's magnetic field can play a role in shaping the halos, channeling the ionized gas and influencing its distribution. Understanding these faint optical halos is crucial for a complete picture of the Crab Nebula's evolution. Now, let's turn our attention to the unsolved enigma of the Crab Nebula's true age, a topic that continues to intrigue astronomers. So, moving on to our 50th and final strange phenomenon, we confront the unsolved enigma of the Crab Nebula's true age. It might seem straightforward. We know the supernova that created the nebula was observed in the year 1054, so shouldn't we be able to calculate its age precisely? Surprisingly, it's not that simple. Despite the well-documented supernova event, determining the Crab Nebula's precise age remains an ongoing debate among astronomers. One of the primary uncertainties lies in determining the exact expansion rate of the nebula. While we can measure how quickly the nebula is expanding today, tracing its expansion backward in time is complicated. The expansion rate hasn't been constant. It has likely decelerated due to interactions with the surrounding interstellar medium. This deceleration is difficult to quantify precisely, leading to uncertainties in age estimations. Another factor contributing to the uncertainty is the initial velocity of the ejected material. Different parts of the nebula are moving at different speeds, and it's challenging to know the precise initial velocities of all the material. This makes it difficult to extrapolate backward and determine when all the material was concentrated at a single point, the moment of the supernova explosion. These uncertainties lead to discrepancies between different age estimations. Based on simple expansion models, one might expect the nebula to be closer to 970 years old, matching the date of the supernova. However, more sophisticated models that account for deceleration and variations in ejection velocity often yield different results. Some estimations suggest the nebula could be younger, perhaps only 600 to 700 years old, while others propose ages closer to 1,000 years. These discrepancies have significant implications for our understanding of supernova remnants. The age of a supernova remnant is a crucial parameter in modeling its evolution and understanding its interaction with the surrounding environment. If we can't accurately determine the age of the Crab Nebula, it casts doubt on our ability to accurately model other, less well-studied remnants. Presenting a timeline of the nebula's estimated age reveals the extent of the uncertainty. We start with the historical observation of the supernova in 1054. Then we see a range of age estimations based on different models and assumptions spanning several centuries. This timeline underscores the challenges in precisely dating such a complex and dynamic object. The factors contributing to this uncertainty are multifaceted. As we have discussed, they include the variable expansion rate, the unknown initial velocities of the ejector, and the complex interactions with the interstellar medium. Overcoming these challenges requires more detailed observations and more sophisticated models that can account for the nebula's intricate dynamics. Despite these uncertainties, the ongoing effort to determine the Crab Nebula's true age continues to provide valuable insights into the physics of supernova remnants. By refining our models and improving our observations, we can hope to one day resolve this enigma and gain a deeper understanding of these fascinating cosmic objects. And with that, we've reached the end of our exploration of the Crab Nebula's mysteries. Now it's time to summarize the incredible array of strange phenomena we've uncovered. In conclusion, the Crab Nebula stands as a testament to the universe's capacity for wonder and mystery, packed with an array of strange phenomena from the unexplained flickering of its pulsar to the enigma of its true age. Each oddity we've explored reinforces its status as one of the most enigmatic and fascinating objects in the sky, challenging our current understanding of astrophysics. As we've journeyed through the nebula's secrets, from superluminal motion to the anisotropic distribution of accelerated particles, it's clear that the Crab Nebula is far more than just a pretty picture. It's a dynamic, complex environment where the laws of physics are pushed to their limits and where new discoveries await those who dare to look closer. We've seen how the nebula's ever-expanding size raises questions about its interaction with the interstellar medium, and how the missing positrons puzzle scientists searching for answers about particle acceleration. From the gamma-ray flares to the unknown source of dust heating, the Crab Nebula presents a unique set of cosmic challenges. Take a moment to ponder these mysteries. What do you make of the strange wisps or the complex magnetic fields? Do you have your own theories about the origin of high-energy particles or the faint optical halos surrounding the nebula? Now we invite you to share your thoughts and theories in the comments below. Let's discuss these perplexing phenomena and explore the possibilities together. And if you've enjoyed this journey into the heart of the Crab Nebula and are eager to uncover more cosmic mysteries, be sure to subscribe to our channel. Hit that notification bell, like the video, and stay tuned for future explorations of the universe's most fascinating objects. The field of astrophysics is ever evolving, and there are always new discoveries waiting to be made. Join us as we continue to unlock the secrets of the cosmos, one nebula at a time.